Okay, I think we reached to this part last time. I think.
Versus one person there.
Yeah, okay, that lady.
Yeah,
Okay, yeah, she usually come a bit late. And I think now let's start it. All right, remember we back to see this, how to solve an equation motion. Once we solve this, it's Newtonian mechanics, right? Once we analyze the force of net force on each particle, then we can solve this dynamic equation, then we can get the trajectory of each particle RIT or Ri dot t, right? So that is the goal, but the difficulty to solve this, first we know those are not independent because we have a stress constraint, right? So if not independent, when you solve this, these n equations, it is not easy because those n equations do not inhibit each other. You have to consider all the other together. So how to solve that? We say that let's introduce the general coordinate. We use QG. So once we use general coordinate, we say general coordinates they are independent. So if we have this and try to find transition equation between this, then we have to figure out how to modify this formula in terms, not this one, but this one. So that is the first way, and we are going to see how to do details, right? Just the idea. So that is we discussed last time, and what is the general coordinates, we had some examples, right? Then now we go to next difficulty. This is much more difficult because we have this force, and we know this is very complicated. Usually we cannot straightforward to write down the expression of force. We just know the effect of force, this constraint, in terms of sum of holonomic and non-holonomic, right? So that is the difficulties. How to solve, we are going to study today. So let's first, this difficulty is here. We know this one is not zero, right? That we cannot ignore that. So in order to solve this, we cannot ignore this one, but think about the other way. Okay, force, constant force we cannot ignore. How about work done by this? So we think about this. This is the alternate idea, and that a kind of critical thinking to help us in later in whatever you have in your future research career, you have some of the difficulties. Try to think of a different way, right? So that is the help us. Let's just think about this. Whatever the night or the wonderful. So how to get this one? So we're going to think about this. How about work done by this? Okay, that is the beginning idea of the analytical mechanics established. So, okay, now if we look this one, so we know what is work. Work is, if we, let's use this, use I constraint, right? So the work done by correspond to the ice particle. On the ice particle, usually speed proportional or whatever the infinitesimal work is the constraint, right? The force due to the constraint on this ice particle, maybe 9, maybe we have several constraints, multiply the infinitesimal change of displacement, right? That is what we are looking for, right? This term. So in order to look this term, let's first analyze or discuss this one, delta R. So the first job in today is we call it a virtual displacement. Delta I. So when we say virtual, say why you use virtual, not the real? Okay, that is a different idea. The virtual is infinitesimal, right? Infinitesimal displacement. And it, okay, yeah. And it is only related to the force, associated the force, which is a time t, not time t plus delta t. So that means if we have this is a virtual displacement, what does it mean? A time t time, right? This is correspond to the force of t. So here, that is okay, let's do this way. That is the chain, right? Infinitesimal chain. That means we just consider infinitesimal chain in that case that the force associated with the system is still a time t. So to understand this, let's consider actual. Compare what is actual displacement. Is usually let's distinguish these both. We use delta Ri. So delta I means what? Okay, suppose a t here, right? A time t, so we have placed the position of an ice particle at Ri. And the force at this position is also t. Then the real or actual displacement after delta Ri, which is a function of delta t, right? Then the Ri from t to t plus delta t, that's equal to Ri at t plus delta, this delta, not this one. It's delta Ri t, right? So you see that is change, and also the force in this case acting on this this position at t plus delta t is t plus delta t. That's the difference. That makes sense? Okay, so with this, introduce this the virtual displacement. Now the second step is we're going to introduce principle of virtual work. So here, right, we consider work. But if the work is the force place or work on this system, just do this virtual displacement, that work we say that associated with virtual work. So now let's see. What is the virtual work? Let's discuss. Principle of virtual work. Since we are interested or focused on work, right? Okay. That is, let's go first. Let's first consider at equilibrium. If the system at equilibrium at time t, suppose at time t, the system at equilibrium. What that means? The system at okay. That means each particle, its net force on each particle means what? How much? At equilibrium. And each particle be zero, right? If not zero, the particle will move. So when we say that at the equilibrium of each particle, its net force on each particle is zero, there is no move each particle, then the whole system is at equilibrium. So that is condition, right? We know at equilibrium. Okay, if this case, then now let's consider if that. So I'm going to use d Wi, which is the force or the net force on S particle to the virtual displacement. So that is Fi net. Right? We are going to look this one, since we are interested to see the virtual work. This is for the virtual work done by this constraint force. Let's consider total. Then we are going to consider separate, right? So that, how much? Is zero, right? Because it's zero, it's a zero vector. So that should be zero, right? At equilibrium. Yes, that makes it zero, no work done on the particle, right? So if each individual particle, the force do the work on this, each individual particle is zero, then the total means just sum of all particles, right? From 1 to n, dwi, and that is sum of from 1 to n, f I nine dot delta r equal to 0. Right, that is where we just consider this case, so we have this result. Okay, we are going to start from here. We know the right hand side is 0, so now let's analyze the left hand side. So left hand side here, okay. F, right? Because F, we classify the force on each S particle is applied and the constraint, right? So we just say, let's separate. Apply. And I'm going to still use net since maybe there are several applied force, right? And space will let me put here. Constraint. So because it's, right, therefore, we have these two terms. So sum over all summation from I from 1 to n, we have two terms, right, if I substitute. So I have first term is only the applied force to this virtual displacement, plus another second term is only this force due to the constraint do the work. Or move the particle as particle to the virtual displacement. So we have two terms, right? That be equal to 0 because left hand side, that is equal to right hand side, no, right hand side. So we have these two terms and together is equal to 0. That means each term is not 0, right? So now we go to the next. Right, okay. Now we are going to restrict ourselves. So yes, we know these two terms, but our goal is to ignore the, or to try to find this term in the formula, new formula such that this term disappears, right? Because this is troublemaker, right? So, or in this case, we want to do this, but now we know this is not 0, we cannot drop, but let's think about this one. So now from this, the virtual principle of virtual work, we can see here, we have these two terms. So now if we just restrict ourselves, the term, second term, this is the work done by this force due to the constraint. Let's restrict that's equal to 0. Then, okay, before then I just say, it holds true in most cases. Later on, when we do some application, you will see. For example, okay, for example, here, this textbook, right? So the constraint, because this cannot move down, right? So it's from table. So this table is normal force, right? Perpendicular to this. So the constraint, the limited motion is along this surface. So you see that delta R is perpendicular to this one, right? To the force. So if perpendicular, then inner product is 0. Even though force is not 0, but this is 0. That is in most cases. The force due to the constraint do the work. In most cases, perpendicular to this delta R. And of course, there are some others, a few cases, but we just consider that means we are going to limit ourselves or restrict ourselves in this case. So then the following, we will develop the Lagrange equation. You know the condition, right? And this in most cases the host. So then now we can have the condition. This term 0. Then this one, we have the summation of this applied force. Here I still use 9. We immediately got this. So this is the so-called this important principle of virtual work. That means all the force, the applied force do the work on the system at equilibrium, somehow altogether is equal to 0. That is this one. That is the so-called principle of virtual work. That is this result. So we are going to discuss this. What is information we can extract from here? Because this just gives us the relation, but as like this shown in the equation of motion for this, we need to get the information from here, right? So now it's from there. Now we reduce, or we move to this formula. Then we are going to understand. We are going to extract the information, right? From here, from this principle. So now let's do. See what kind of information can we get. You always keep in mind, even though we ignore or restrict this one, but does not mean we ignore this force. The force due to constraints is very important. We are going to include that, and you will see how to include this information. It's from the equation of constraint that we learned last time. Okay, so now, and then now let's discuss this. That means we are going to understand this, what it means from this formula. Okay, first, I still want to emphasize, we know this definitely is not equal to 0. Right? Applied. Even at equilibrium, right? When we say at equilibrium means this force is include both, right? This one plus this one equal to 0. So the applied force even at equilibrium not equal to 0. And also the force due to the constraint is also not equal to 0. The both add together is 0, right? So that be careful here. That's the first thing we want, but we limit this, the virtual work done by the force due to the constraint is here. Or we just restrict only a constraint. only for this case. If this case holds true. This one, right? These two are not there, but this one is restrict. The second one, that is very important, and then we are going to see how to include this force due to the constraint into the formula. This one. Delta R, are they independent? No, right? Are not independent. That is very important. So be careful here. If independent, you will see, okay, then this formula becomes very simple. If this is independent, that means this force is independent, right? That's a linear independent condition. If this variable are independent, so the coefficients will always equal to 0 to make sure they are independent. But if not independent, that means this also not 0, right? Mathematically. So here, that is the next issue we're going to discuss. If not independent, okay, and three that this formula still want to remember we had just discussed at equilibrium, right? If not equilibrium, this is not hold true. So I still want to just keep in mind this one equal to 0. This principle of motion work is only at equilibrium. So these three, be careful. Okay. Now we are going to deal with this one. Yeah, let's deal later together. So we are going to deal with this one, as we said that we introduced the general coordinates, right? So we are going to deal with this and to substitute to here and see this formula how much information can get. But since this is only at equilibrium, we are going to consider at non-equilibrium. Okay. So I think system. Okay, now let's consider non-equilibrium, right? So let's first consider this one. So if the system is at non-equilibrium, that is normal case, right? Then how to deal with those? Let's see. Okay. If not, according to the either Newton's second law or this equation of motion, for each particle, right? We know this, right? Okay. So this is at the not equilibrium because net force is not equal to 0, then it will drive the particle move, right? And how the particle move depends on how the net force. So because this, therefore, let's do this one. I'm going to move this to left hand side. Here, this dpi dt is pi dot, right? That equal to 0. So that is interesting. What that means? So if we have this is a real force exert on the S particle, the net force. Now we have another term we call this one, the negative sign plus this one, reverse effective force. We call this. If we give this is because this is the determinant or the measure is the same as force. It's Newton, right? And then that be a kind of force. We give a name, reversed effective force. It's not real force, it's a kind of effective force which we can consider as a kind of force. So once we have this, that means even systems does not equal to, or each S particle is not at equilibrium, but if the force on the S particle is this real net force plus the reverse effective force, then that gets 0, right? So that is the important. Okay, if that's 0, then we can apply this. Since this, yeah, I think, okay. And I'll apply this one, right? I think it is here, yeah, this one. Before I separated the force into the apply and constraint, but this is the principle which, so therefore, we have immediate, I will not go to the details we have immediate because this is 0. So the summation, that's immediately have this, right? Summation of this force, because this is 0, minus this pi dot delta I equal to 0, right? Since this is 0, this is 0 vector, right? 0 vector multiply or in inner product with any vector is equal to 0, then summation is also equal to 0, right? So we immediately got this. Now we are going to work on this term. Here, the difference between this one and this one is we have this one. And another term we call the reverse effective force, since that is the dynamics of linear momentum, right? So now we are going to do this. Let's do this step by step. Then we are going to derive so-called the Allenberg principle, and then finally introduce Lagrange and the Lagrange equation. So now let's start here. Again, we are going to apply the force, and that force has two terms, right? So then this one we can write, separate this one by applied force, right? Applied. And this one, reverse the effective force together as one group. And then the remaining second term is only the work done by the force due to the constraint. This be equal to 0, right? So this is just work on the left-hand side. Then we are going to again restrict ourselves. So since I have here, okay. So that is from here to here, just substitute or classify the force into two parts, right? Then again, if we still restrict ourselves, that only consider the force, the work done due to the applied force, but the work done due to the force by the force due to the constraint, we restrict it is a 0 case. Then we can immediately get this result. So that is applied force only. So applied force we can analyze, we can have this expression, right? That is, we know, familiar. And here we have the reverse effective force, Pi and dot delta R, right, equal to 0. So now we reach to here. If you compare with the principle of virtual work, here the only applied force, that is at equilibrium. Here is at non-equilibrium, we have another term here. So now we are going to do the detailed analysis or how to get this information or extract information from here. Now, the question here, same thing. Now we are going to extract the information or the discussion, right? Okay, discussion first. Here, we know now in this case, so this term, the force due to the constraint never appear, right? Never appear. Yes. So now we work on this one instead of work on the equation motion of equation of motion. In that case, should be total force. Here, if we restrict the case that this force due to the constraint do the work is 0, then we are working with this. So we are going to find or extract the information from here. Then that means, yes, up to here, we reach our goal, right? We want to get rid of this information directly from the false due to constraint. But it does not mean we ignored it. We are going to consider this effect due to, so here, that's never appeared, but the effect of this constraint due to this force due to the constraint is included to where? Remember last time we discussed equation of constraint, right? Into the equation of constraint. For example, for the holonomic, we know the function, it is a function of, okay, I think either x, y, z or r, right? So let me just make, yeah, let's just x1, y1, z1, and x2, y2, z2. I just use r. I think you know that r is vector, right? R1, R2, Rn, and maybe time dependent explicitly or implicitly. Alpha, we have how many? Alpha from 1 to k, right? So, even though we ignore or this force never appeared in this equation, but it does not mean we ignore the effect of this. Those effects include in the equation of constraint. So that is the most important first information we have to understand this from here. Do not worry that. Okay. Second, again, the delta R are not independent each other. Okay. So we are going to extract information. Okay. So now the second, as I already mentioned over there, are not independent. Okay, not independent. So how to do that? Due to here, right? So if not independent, then means you see here, this means this two force, apply force plus this reverse effective force to the inner, with inner part of the R sum over together 0. That means, but this, since they are not independent, so this one is not 0, right? Now be careful. That does not mean this one is not 0. If independent, then this coefficient should be 0. But since it's not independent, so we have this one is not 0. The only means this one do the work, sum all together is 0, right? So that is important. All right, so that is, okay. And this, of course, you consider if we have n particles. So we have n formulas, that is this one. Now the third one. So now we are going to go to the details. First, we just know what is the condition, what is the background. Now we are going to do this, extract information from here, how to get. So now, this can only for the holonomic constraint. If not, then we need to discuss later, right? So let's just focus on the holonomic constraint is like this. The function or equation of a constraint only function of the position and maybe implicit or explicit depending on time equal to 0. Even there's no any function dependent on the velocity of these particles, and not equal, like a larger or equal or some others. That is non-holonomic, right? So we just consider holonomic. So we have, let me write down again, this one, right? Okay, I think that the condition of the equation of a constant is R I, that is R1, R2, Rn equal to 0. Alpha, how many we do not know, it depends on different systems have different equation, how many constraints, right? So we have one constraint, we have one equation. So that is for this one, we will have introduced, as we discussed last time, we can introduce general coordinates, right? So how many GL from 1, 2 to how many n? Lower n. That means lower n gives us a total number of degree freedom. For the system, we have how much? So how to get n? Remember n equal to what? If we have n particles, each particle has x, y, z, 3 degree freedom, right? So if there's no any constraint, it's 3n, right? Then how many constraints? Alpha, we have a k, right? So minus k. That is total number of degree freedom, right? Last time we already discussed and have some examples. So now you deal with this independent. So now we are going to the details. Let's just consider for holonomic constraint. We are going to select a side of the general coordinates. How many? Lower n, which is number of degree freedom. How to determine that? You are going to find number of equation of constraint, then you 3n subtract, right? So that is, so once we have this, okay, for this, then once we introduce general coordinates, so we can write down then the transformation equation between the general coordinates and the ordinary coordinates. Transformation equations, right? So R, just Ri, the ice particle, the position of real position, right? Ri to be function of general coordinates q1, q2, until qn, and maybe also function time. So here I from 1 to n, right? We have n particles. So each particle, the position has this equation we call the transformation equation. Remember we also discussed last time. It's a function of general coordinates. How to write this one, we also do some examples, but later we are going to do more examples and let you know how to get this. Once we know the equation of constraint, how to get this transformation equation. So once we have the transformation equation, okay, now, actually, since this vector, right, you have xi, yi, ji, total equation 3n, right? So that is, now we are going to, since here, we are going to replace this, delta Ri, right? This equation, since this is not independent each other, so this equation cannot give us further information since we cannot get direct this is equal to 0. So we are going to see from this equation what kind of information we can extract. Now, we are going to replace delta Ri in terms of the general coordinates. Then this became a general coordinates, then that is independent. So we can find all the coefficient correspond to general coordinates to be 0, right? That is the next step. So now, in order to get the delta R, so, we need to find this one. Since we have transformation equation, R is a function of Q, right? I mean general coordinates are Q1, Q2, and Qn at time. So be careful, this is now, I know you have a strong background in math, so if a function is, the variable have a lot of variables, so this means the partial. Okay, I take a name. Partial differential. Yes. Or do this. So we just use some notation, something like this, right? So that means only change R with respect to the general coordinates does not depend on time. How much? If you have this is a function of n variables, so when you do this partial differential, that means you have to do all the variables change, right? So that's summation. Now the variable is j, right? J from 1 to lower n, partial Ri because Ri is a function of Qj, right? So, and partial Qj, then either use usually we just follow the delta Qj, or because partial delta sum is sometimes the equivalent, so we do this. Okay, be careful here. That is because we change this one means change each individual general coordinates, and the total together must be equal to total change of delta r, right? Any question? Okay, so this one, dri. This be total differential, right? Total differential should be total change with each variable change, right? So that's be first change of this the general coordinates. So here, be careful. This is j. This is lower n, partial ri, partial qj, delta qj, and ri also function of time, right? So there's another term. That is total. So you see the difference. So total dri actually is delta ri plus this term. Partial dt for ri with respect to time. Okay. So this is sometimes mistake may happen. So now I just want to emphasize. Now once we have this, we are going to do, what is this one? Dri dt, total differential, total change of the r with respect to change of time. So we have to start from here, right? Okay, that is sometime later we are going to use this notation, ri dot, but the dri dt is total time differential. Okay. If you give a name, this is a total time differential, right? That equal to, since now it is a function of a general coordinates and time, right? So again we have, let me use, okay, I think here I still can use G notation here. Let's use G again. Sometimes if we use the index, they both are Fij, not G is the particle. So here we still, in general, we use as an index for this general coordinate. But later, if we have a conflict, we are going to use another. So from 1 to n, right? And then, like this, partial Ri, partial Qj. Now here, dQj dt, right? And plus this one. I think I forgot this one, right? So that is, here is partial Ri, partial T. Okay. Yes. So you can also write, since this is a time digit of the general coordinate, then we can also rewrite this. Later we are going to use, to make a symbol, we do it easier, Qj dot. Okay, we are going to use Qj dot means this, right? And partial Ri, partial T. So this is the formula of Ri dot. That means sometimes we may miss okay, this one. So that is one. Now, another important relation here we have to see. Partial Ri dot, partial, in this case, I'm distinguish, I'm use K, Qj dot, Qk dot. So this term, since later you will see in the Lagrange equation, we always use this term, but we will see is equivalent to another one. So now let's do that, because that's important. We're going to do. This is partial, okay? So here, Ri dot is this one, right? So this again is a function of, you see here, is a function of Qj dot, and T, right? This Ri only function Qj and T, but the Ri dot also, in addition to the Qj T, and also have a Qj dot, because here, right? So that's why we do the partial. Then you can see if I do the partial Ri dot only function qj dot is this term. There's no qj dot here, right? Because you know that Ri is only qj and t, right? So if we do this, nothing. And this one, how about this one? This term. Does it depend on qj dot? Yes or no? No, right? This is a Ri, you see Ri is here. Only qj and partial q, does not partial t, right? So that is also, so then you mean this one is only for this term. So you can immediately here, I'm going to use this j from 1 to n. I keep this term. J. This term, because this term does not depend, and this one, so that's partial qj dot, partial q k dot, right? And this term disappears since it does not include this. And here, this only, because this is independent, right? So only when j equal to k, right? So this term, if I write intermediate, I hope you can understand. Partial qj, delta kj, right? Only k equal to j is non-zero. So then the summation for all the j, then only j equal to k, right? So then became r partial ri, partial qk. This is very important, so I would like you to remember this. This is a dot, right? Partial I, ri dot, respect to qk dot equal to partial ri, partial qk. That is very interesting. And with this, we can make the formula later we are going to derive. You will see, make it simple. Okay, so now I think this term we already discussed. Now we can go to the formula. Go back to here. Since here, right? So since we are going to deal with this one. Okay. So now go back to this one. Let's first look at the first term. Since we have two terms, right? There's two terms. Let's do one by one. So let's look at this first one. Look this. So let's see discussion. How many one? Three, right? So now that's 4. That's 4. The first term. Let's consider this one first. We do not know this is not equal to 0 because we have another term, right? So we just look this one. Then here, and we just use equal to here. So here we are going to replace this. It's here, right? So, and write down here and I from 1 to n particles, and the force, applied force. Okay, then applied force now here. Delta Ri is summation for j, right? So now summation j from 1 to n, and the partial Ri, partial Qj, delta Qj. Right? This part is delta Ri. We just put here. So now you can see delta Ri is only here. Now you can see we have two summation, right? This one does not depend on j. So I'm going to, but this one, Ri depend on, Ri, this one depend on I, right? So I can take the summation for j outside, partial Qj, and inside here is I, this depend on I, so I cannot take out. So inside is I from 1 to n. The applied force, net applied force, now here is not delta R, but it's partial Ri, partial Qj, right? And outside is delta Qj. So you see this term. This term we have an inner product between the applied force and this gradient or partial derivative of Ri with respect to the general coordinate. So after summation for Ri, this is be something only depending on J, right? That makes sense? So here, let me see, we are going to introduce Qj. So this term, if then we are going to discuss Qj. So here, I can write down this. The first term is Qj. This inner product gives us this scalar, not vector, right? So you see here now vector disappeared. It became scalar. See, the first term very simple. But now since we introduced Qj, let me give us the definition. Qj is sum of all these terms in particles, right? Applied net dot partial Ri partial Qj. We call this generalized force. The reason why it's generalized is not force. If you look at the dimension, right? Okay, J's components, right? Because it's dependent on J. Now you can see different J, different term. J's component of generalized force. I give a name. Qj, capital Qj. So that is definition. So here, J, you see the J, how many? 1, 2, 2, n. Number of degree of freedom. So how many degree different? The degree of freedom will have how many components of these general coordinates. Okay, so this is a definition here. This one, it might be the general, the force, general force might be the force, okay. Might be the real force if this the general coordinates are positions, real positions, like I, x, y, g, right? So in that case, you will see here, if this is a dimension, it's meter, right? This is meter. So they cancel. Then this force is, this unit is Newton. This is also Newton. So in that case, it is force. But torque, if in this angle, right? So torque, if are angles. Then you see here, this is a meter, this angle's degree, and you can see that is torque. You know torque is force. Cross products are, so the dimension is Newton with meter, right? So you see, now the general means does not mean there is real force, and maybe power sometimes if the general coordinates are kind of term, right? So not correspond to terms like pi in some case. So that is really depend on what kind of general coordinate you select, and the general force is also changed. But the products, okay, here, this is general coordinate multiply the general force multiply general coordinate. This always is work. See the left hand side. This comes from here. Okay, if it's from here, right? This is work. Force in the product is displacement. So this dimension is always work, and this term is come to here. Right? So first time write down in terms of the real applied force with the real virtual displacement, now replaced by the general force multiplied the general coordinates. This product will not change the dimension, right? So that this is we want to see here. And now this is the first term we discussed. Now we go to the second one, right? Second one, I think, if not, I think you remember, right? So okay, number 4, number 5. for the second term. So if you remember, we have ignore this negative sign. We are going to add that one and add together. The second term is this so-called revised effective force, right? Pi dot inner product delta Ri, right? So let's look at this term. This term is not equal to 0, but we know, let's see how much. Again, we are going to replace this one and this one. So delta Ri is here, right? And Pi dot is dri, dri dot dt, right? So now let's read, right? Dri dot dt, inner product of delta r, we are going to replace delta ri by this partial differential. That is the partial ri, partial qg, delta qg, right? Again, let's move this summation for g outside. And then here, okay, inside summation for I from 1 to n, I think I have a mi, forgot, right? Sorry. The pi is mi dr. Okay, so that is mi, all right? And here dri dot dt, and here this one is inner product here because it's vector, right? Inner product partial ri, partial qg, and outside is delta qg, right? So now let's look at this one. Let me look at this one, right? Inside the summation for all the all the I, what does it look like? So now let's analyze this summation. Mi dri dot dt inner product partial ri, partial t. Okay. Let me write down the result and I can help you to understand why I write this. That is equal to d dt. There are two terms. Is r dot inner product of partial r. Partial ri, partial qj minus r dot d dt partial r partial qg. Why? Okay, let's look at this term. Because if we do the total time derivative of r dot inner product with partial ri, partial qg. So we heard first, this is the two terms, right? We can do the first one is dri dot dt inner product of partial ri, partial qg, and plus ri dot with d dt partial ri, partial qg, right? Do you have it? We do the total time derivative of these two terms. So we do the first, keep this one, and do this total time derivative. Okay. So then this term is this one, right? This one is this term. So we just move this to the here. That means this term equal to this term. Subtract this minus sign because this moves to the left hand side, right? So that is give you why I write down here. Now you see the dt does not depend on the summation. I can take outside. Okay. So okay, just give you the easy. So now I keep continue equals here to here, right? D dt, because these both are dt, total time dt, so I can put outside. And then there's inside, okay? Let's do this one first. So this is dt, so now inside here, this is q. Okay, all right. So now, I don't want to jump too much. So now here, let's still keep here. 1, 2, n, m, I, and d dt ri dot partial ri partial qj here equal to this. So now we use this solution. Okay, so that is here partial ri dot partial qj dot, right? And the second term is summation I from 1 to n, and ri dot d dt partial ri partial qj. Here, I think I can also replace that by this. Replace that by. You see this one? Okay, let's do it. Both here partial ri partial qj, here partial ri partial I replace by partial ri dot partial qj dot. Okay, so now then we can do this. Here the first term, take this outside, so now let's see d dt, and here this one also have a partial, right? So 1 over partial qj dot, and the remaining side inside is summation for this I from 1 to n mi r I dot partial r I dot, right? The first term, and did I miss something here? I think instead of do this, instead of I think this one, I do not do this. This is sorry, this one already here is partial qj part, this is r, this is dri dt, right? This is ri dot. Partial here, partial ri dot partial qj. Sorry, the second one. So second one I do not replace because this we can interchange, right? Partial ri partial qj. I can first do the partial ri partial t and then partial qj. So this can exchange. So I do the first. Then partial ri dt or dri dt is ri dot. Then this partial come to outside. Partial this ri dot partial qj, right? So we have this. Then this one. Now I take this one outside. Yeah, and then this one's here, and this I put here and minus here, right? Minus qj. Okay, 1 over partial qj. Since this does not depend on I, and inside summation I from 1 to n r I dot in the product of delta r I dot. Right? So you can, I mean math. So you see here, these two terms are same, right? Okay, now we want to know this, what is this term. We're going to know what this term means. If you probably already know what is. Okay, let's consider this total energy. Sorry, kinetic energy. Total kinetic energy is sum over all I from 1 to n, half of mi ri dot square, right? So the partial t is summation y from n to n half of mi. Then we have a factor, sorry. So do the partial Ri dot square with, that is we have a factor 2, right? And Ri dot and partial Ri dot, right? So this cancelled, that is I from 1 to n mi. So you know this term is nothing but this partial kinetic energy. That is the term here. Because this, so now we can finally which term? This is our fact initial, right? So now let's write down. So this second term, pi dot in a product dot I dot is equal to, now we come down to here, right? dt, ddt, okay, and now the partial t, right? Because that term is the partial t, this one, and the partial qj dot. Second one is partial t, partial qj, right? Here, this is a partial t, this is partial qj. So, see, this second term, I think if you probably already learned the Lagrange equation, right? Something like this already come up, right? Very good. So now, then we have to combine the first term. So now let's sum it together. This equation is so-called the D'Alembert principle. Now we sum it together. So finally, that is 5 now, 6. Finally, this is summation I from 1 to n. I is only applied force which we can get the expression straightforward. And this one is this dynamics or linear momentum about dynamics. Delta R equal to 0, right? Now it's reached 2, so now if you remember the first one is summation j from 1 to n, lower n, this one, right? Qj, delta Qj. Remember this term right here. Minus, here we have minus. And this one, d dt, partial t, partial Qj dot, minus, this minus became plus, right? Partial t, partial Qj equal to 0. And now how many equations? Lower n. That's why we have n degree of freedom, which is n independent general coordinates. So now you can see here. I think I missed somewhere. Did I? This is one. Yeah, here I missed this one. Remember this term. So that is this one. Okay, here. Summation. That is one. I just analyzed one of terms. So now this is summation j from 1 to n. Right? That is this. So now here, okay. Give a space. Minus summation j from 1 to n, d dt, partial t, partial q, j dot, minus partial t, partial q, j. Look at this. Now you can see this is a summation for all the qj, but qj independent. So let's rewrite. I put all together. 1 to lower n, q capital Qj minus d dt, partial t, partial q, j dot, plus partial t, partial qj, delta qj equal to 0, j from 1 to n. Since this is an independent, then we can immediately get this. Therefore, this coefficient should be 0, right? since these are independent and sum over all these together equal to 0, any case, no any kind of special condition, in any case it's equal to 0, then what happens? Since these are linear, so we have this Qj minus d, each coefficient should be equal to 0. Plus, if I use, okay, so if I use, okay, I use plus, this all together, right? Plus partial t partial j equal to 0. Then we move this term to the another side. So now we can summarize. Finally, we have d dt partial capital T, the kinetic energy partial Qj dot minus partial T partial Qj equal to Qj, j from 1 to n. This we call the Allenberg principle. Okay, so that is the Allenberg principle. And or we call it differential principle. Since in chapter 2, we are going to use the integral principle or Hamilton principle, we can also derive the equation or Lagrange equation. So just depend on different way. The Allenberg analyzed from this differential equation or equation of motion, right? That is P dot equal to Fi naught. So that is this one in general. So far here. So now we can do further discussion. Let's consider the force if here applied force, right, is here. We do not need to consider any force due to constraint since this disappeared. So if these all the applied force are conserved force. If not, then we can separate some of conserved, some non-conserved. But let's consider the first case. Are conservative. Conserved forces. So now let's see what can, how can this equation go to further information. So here you can already understand. Okay, that equation or from the principle of virtual work and for the non-equilibrium we already derived the formula, and from that formula we extract up to here. So here you can see to analyze the dynamics we do not need to analyze force. We just need to know the kinetic energy. And the kinetic energy you know that is scalar, that is easier for you to write down. Of course, the force information here. So now we are going to discuss it with you. Since here this is not 0, right? So now, okay, let's consider if this conserved means this one we have 2 parts. One is external applied. Since external is applied, so except for all constraint we call applied, right? So I just write the external plus internal, right? Internal I not equal G F and G, right? Or Gi. This is the G to the I, right? Gi. This is internal. So that means in that case, suppose all the forces are conserved force, then the on S particle, the net force come from external and internal. So now both are conservative. So if both are conservative, let's see, we already discussed right in the beginning, so I think I just omitted right down here. So then the external, for each one, this is summation, right? So each one is negative, the gradient of, we have external potential, right? Yeah, let's use R. For each external force, we know if it is a conservative, there must exist the field potential. I use VI, and the force is gradient, negative gradient of this potential, right? So that is this one. Then let's see the force, the generalized force. Okay, so now let's look at this term. the general force, we have this is I from 1 to n, F, okay, external I is a partial Ri, partial Qg, right? Remember, I erased, but I think you remember this term is F applied. And apply have two terms, so I just look at this first one, right? So you see here that equal to minus summation I from 1 to n, delta I Vi external, and inner product partial Ri, partial Qg, right? Reading is partial Vi, partial Ri, right? So these two cancels, then you will see this minus n, okay, partial sum over all, right? So that the partial V, I'm going to write down this, okay, then partial Vi, external, partial Qj, and then partial total external potential, partial Qj, so the V total external, just sum over all the external field. So that part means if the applied force has two parts and all are consecutive, the external part is nothing but the general force. Generalized force is partial the external potential, total external potential with respect to the general coordinates. So that is, okay, I think, let me just, I think that very quickly I'm going to finish this, occupying a few minutes. So that is this case. Then that also, now go to this one. Fgi is minus, if you remember, we have already derived Ij, potential Ij, right? This internal force has another external potential, the field, potential field, and the external inaction, the force is negative gradient of this. We already know now. So then here, this part, summation of I from 1 to n. Okay, that's fine. G. Oh, all right. So now I want to distinguish here. So this one, since this this force is here, right? We have summation I. For given I, we have sum over J not equal to I. But if we found total I from 1 to n, so we have a J also from 1 to n, but J not equal to I, right? Fji. This is another term which is, I want to distinguish, now I have to distinguish. So this is general, I'm going to use K. That is why I say in this, only in this case, we consider interaction between the particle, that is the internal force. We have Ij is all indicate as the particle, then the general coordinates, the index, we use K. So in this case, then you can see here that is the summation I from 1 to n, and J not equal to I. So here, negative Ji, Vij, inner product partial Ri, partial Q. Okay, right? And you can see here, I think we already did something similar, so I will not go into detail. Here, this summation, we can write in pairs. So for the I from 1 to n from J, because this all appears Ijji, right? So here, partial I, Ri, and another partial Ij. Sorry, Rj. Then Ra, Rj here, you know this, the force, delta Ij, Vij equal to negative delta Ji, right? Because force is a weak inaction law. So I immediately write down here that is equal to, okay, because then we have a half, right? Since we have pair, each term has two terms, so then those two summations became half of summation. I from 1 to n, G not equal to I. And here it is partial Vij, partial Rij, and this delta Rij partial Qk. This here, this Rij is because I have two terms together, so this one is partial Ri minus partial Rj. So that is the partial Rij. Is this term? Then I have a factor 2 here. Then you can see here this minus half of I from 1 to n and g not equal to I, yes. And then it's a partial V and G, partial QK. Now QK does not depend on IJ, right? So then we have, okay, that is one term, right? Then we have this is one term. Then we have a summation, that is summation from the QG is summation from G from, this G now I'm going to use K, since we have already used IJ here. So the QK is a K from 1 to n, QK, I do not, because we have two terms, right, external, so now let's say this one. QK is summation I from 1 to n, G not equal to I, F, G, I, partial Ri, partial QK. So this term is become here minus a half of summation K from 1 to n, and then this one is, I'm going to give a summation right now. Okay, yeah, already here, right? So that means I put all together, since this does not depend on K, I'm going to say partial V internal partial QK. Sorry, remove this half. So the V internal is defined is half of sum over O, I from 1 to n, and I not equal to J, V and J. Because I observe half into this here, and the Vij is here. So this sum over all together, in this case, does not depend on K. Then I put partial QK outside. So this summation is this energy, right? So now you see, finally, what we have? This is the second term. Now let me write down the final. So I think we can stop here. Yes, so Qj equal to that is the total Qj, right? Okay, so that is Qj. Now I go back to J. Okay, since here we have observed this idea together inside this one. So Qj is partial minus V partial Qj, J from 1. This is an index of general coordinate. So V is V external plus V internal. Internal here, external here, right? So what you need analyze potential energy, external potential energy, and the internal potential energy. So right down here, then you have a general coordinate. False. Okay, let me just stop here, and then we substitute into here. This is almost, you can see. Too much, I don't want to. Yeah, okay, let's continue on Thursday. But we almost reach here, since we already have this formula. If this conservative force is very simple here. Okay, you have question? Yeah. All right. Do you have any question?